Okay, so the plan for today is to finish up the last couple of examples on 7.6 quadratic equations, and then to start into chapter 8, really the last chapter that we're going to cover in this course. Note that the Unit 2 exam is this week. It's currently available on WebAssign. Uh, oh, I have that there. It's currently available on WebAssign. Uh, the sample exam is also available on WebAssign. So that should give you, the sample exam will give you a good idea of, um, the length of the exam, the material that's on it, and so on. Um, it is due this coming Sunday, the 27th at 11:59 p.m. And just like the Unit 1 exam, I would strongly recommend that you plan to complete it on or before Thursday. That way, if anything does go wrong, you have a bit of a buffer. There are no due date extensions on the exams. And then as we get close to the end of the semester, I like to just kind of lay out a roadmap of what the last few class meetings look like. So the next three meetings, so this Thursday, and then this coming week, Tuesday and Thursday, we're just going to be continuing through chapter 8 on rational expressions. And then after that, we have final exam week. So it's going to be a pretty quick turnaround. Um, I know this is kind of a crazy time of year, lots of, preparing for final exams, projects, labs, all of those kind of things popping up around the same time. So I like to give you a little bit of a roadmap so that you can see what's out there and what to expect. Um, Note that the final exam I'll have available from Friday the 2nd through Friday the 9th. So I'll actually make it available a little bit before the official final exam week. And really the reason for that is, especially with remote classes, I know that a lot of folks take remote classes because of logistics and things like that. So that gives you a full weekend to work through the exam if weekends work better for you. Um, so I know that, Friday the 2nd is pretty close after our last class meeting on the 1st. But it is what it is. It's kind of crunch time at finals time. So if you want to use that weekend, you're welcome to. Of course, if you want to wait until final exam week proper to take the exam, you're certainly welcome to do that as well. But with the same caveat, don't wait until Friday afternoon or evening to take the exam. You do not want to put uh, you know that much of your course grade in jeopardy, hoping that nothing goes wrong and there are no issues, anything like that. I would recommend planning to complete it on or before Wednesday night, and that way, if anything does go wrong, you've got plenty of buffer to work with. It'll be basically the same format as a unit exam, taken on. Why did I did not proofread this well enough when I copied it over. So it'll be taken on WebAssign, not using Examity, of course, because uh, our system is not working very well this semester. So it'll be taken on WebAssign, similar setup to the unit exams. Um, you'll have 2 hours for the final exam, and it will be comprehensive, so it will cover all of the material we covered in the course. Sample final will be available the week before, so roughly a week or so from today, or actually probably at the end of this week when I'm looking forward to next week, I'll probably just pop that sample final up and have that available for you so that you can, see what's going to be on the final exam, start studying for it, and all of that. But the actual final won't be available until Friday the 2nd. Okay. Any questions on any of this rundown for the rest of the semester? All right. The quote of the day today is it's a quote that's often attributed um, to the Roman Stoic philosopher Seneca. I don't know why I had so much trouble remembering the word Roman. I wanted to say Latin, but that's not right. The Roman Stoic philosopher Seneca, or Lucius Annaeus Seneca. Um, but as far as I can tell, I don't think that there's much evidence that he said it. So who knows who said it, but I think it's an interesting idea anyway, that luck is when preparation meets opportunity, right? So you look at somebody who's maybe in a position you want to be in, and you say, oh, I can never get there because look at these, half dozen things that happened throughout their life. They were just very lucky. And I think, something that we miss is that opportunity kind of comes around from time to time for everyone. If we're prepared to meet that opportunity, then that nice confluence of events, the preparation and the opportunity that came around, allows us to move forward substantially. What chapters are on this week's exam? I'm pretty sure it is chapters 5 through 7. Let me double check that. Yes, chapters 5 through 7. So we are wrapping up the last tiny bit of 7.6 today, but we already really covered quadratic equations last time, and this is kind of just a couple more examples in that vein, and then also somewhat of a bit of a warm up for chapter 8, which also is going to deal with quadratic functions. But yeah, so we have this nice confluence of events when an opportunity comes around and we're prepared to meet it, right? Yeah, so we can't really do a ton about how often opportunities come around. I suppose you can, if you want to be a Hollywood movie star, well, living in Pittsburgh probably isn't going to give you many opportunities for that, but maybe moving to LA will give you more opportunities. Or if you want to be a country music star, maybe moving to Nashville will afford you more opportunity for that. But mostly what we can focus on is preparation, right? And that's part of what you're doing here is getting a degree prepares you to meet opportunities, maybe that come around in a career field that you're interested in. And looking back, you might see, oh, well, that was really lucky that, or fortunate that came around at that time. But had you not been prepared, you wouldn't have been able to take advantage of that. So I think this is a nice quote because even though, it's I think most would agree that, in some instances there are more opportunities that come around, or in some instances there are fewer opportunities that come around. Most of the time, what we can handle is our preparation. And if we make sure that we're prepared when an opportunity comes around, we can take full advantage of it. And no matter how many opportunities come around, if you're not prepared when they come around, you can't take advantage of any of them. So that's really what mostly is under our control. Okay, so oh, what happened to my, sorry, let me pause my share for a second here. I had a last couple of examples from 7.6 and I either didn't copy them over or something went awry here. Give me 1 second to get this lined up. This is what happens when I plan too far ahead. I was trying to get all of the rest of my semester laid out, so I have all of my notes ready to go and all of that. And I swear that I remember copying this over. So I remember exactly which example I started with. What should be like at the bottom of this page or something like that. All right, I don't know if I copied it onto a different day or what, but all right. So these are just a last couple of examples and exercises in solving quadratic equations. Again, just as kind of, to kind of wrap up that section, but also as a bit of a refresher on quadratic equations before we jump into chapter 8, which will use some of the same ideas. Okay, so let's look at a couple examples. Now, one thing we had talked about in quadratic equations is if we follow the philosophy of linear equations, if we say, okay, I want to try to isolate the variable and then go from there, so get the variable terms on one side and the constant term on the other side, I'm kind of immediately stuck. There's not a whole lot that I can really do here. Right. I mean, I can't just like take a square root. If I didn't have this minus 5y, maybe I could get away with doing something like that. But I have the minus 5y there that's kind of messing things up. I can't just like divide by minus 5. If I didn't have the y squared here, this would just be a linear equation. I could do that. That would be fine, but that's not going to work either. Really, the approach here is, um, I would say, actually fundamentally different than solving a linear equation. So first, we're going to try to get the quadratic equation in standard form. So we want to get actually everything on one side. We want to get a bunch of stuff equals 0. So I'll do that by subtracting 7 from both sides. Why is it so important that I get something equals 0? I mean, if I subtracted 6 from both sides, would that work as well? Not as easily. So why is this so important? Well, the reason is that if I can factor the left-hand side, let's just pretend this isn't going to work, but let's just pretend it factored into y minus 2 times y minus 3 equals 0. Well, now what I really have is one thing, let's just call it a, times another thing, let's just call that b, equals 0. But I have a zero product property. It's a very specific property that applies to 0 and not other numbers like 2 or negative 12. That if I have two things that multiply to make 0, at least one of the two things must be 0. So then either a is 0 or b is 0 or both. Or in other words, either y minus 2 is 0 or y minus 3 is 0. So that is my strategy. I'm trying to make use of the zero product property after factoring to help me here. Now I look at this and I ask myself, okay, does y squared minus 5y minus 7, does that factor over the integers? I notice that minus 7 is either has to be plus 1 times minus 7 or minus 1 times plus 7. Do either of those add to minus 5? This adds to negative 6. This adds to positive 6. Neither one adds to the cross terms coefficient of minus 5. This quadratic is actually prime. And so our approach isn't going to work. So we really can't move forward here with this problem. What about this one, though? A very similar looking problem. Y squared minus 5y equals 6 instead of 7. In this case, on the left side, well, 6 can be 2 times 3 or 1 times 6. We need to have opposite signs, so they multiply to make a negative. So I could have minus 1 and plus 6, plus 1 minus 6, or minus 2 plus 3, plus 2 minus 3. And I'm looking for one of these that gives a sum of negative 5. Be a little careful. We have like minus 2 and plus 3. So they don't give a sum of minus 5. Minus 2 and minus 3 would add to negative 5, but they would multiply to positive 6. So I think the answer here is actually minus 6 and plus 1. Those two multiply to negative 6, and they add to minus 6 plus 1 is negative 5. So I get y plus 1 times y minus 6 equals 0. And now, again, I have this product of two things equals 0. That means that either y plus 1 equals 0 or y minus 6 equals 0. So I've taken my quadratic equation and I've broken it into two fairly simple linear equations, right? Something we often like to do in math. We like to take a big complicated equation, we want to break it down into multiple simple problems and then break each of those into multiple simpler problems. And, we end up doing like 15 really simple problems to solve one really complex problem. If I subtract 1 off of both sides, I see y equals -1, or adding 6 to both sides over here, y equals 6. So my answer is y equals -1 or y equals 6. There are two solutions here. Remember, quadratic equations have, at least kind of in their, let's call it like typical or standard or canonical case, they have two solutions. And we see the two solutions here. And then lastly, let's look at this third problem. X squared minus 2x minus 8 equals 0. That's already in standard form. We're ready to proceed with trying to factor the left-hand side because I have a 0 on the right-hand side already. Okay, so what am I looking for to factor this? I'm looking for m and n such that m times n is -8 and m plus n is -2. Their product being negative says they have to have opposite signs. Their sum being negative says that the larger has to be negative. So let's list out some m's and n's that could multiply to 8. We'll forget about the sign for the time being. That's 1 times 8 or 2 times 4. And then we have to have opposite signs with the larger being negative. So +1 times -8 or +2 times -4. And what are the sums? M plus n. -8 plus 1 is -7. -4 plus 2 is -2. And that looks like the right option. So coming down here, I see that x squared minus 2x minus 8 can be rewritten as x plus 2 times x minus 4. And that's still equal to 0. And once again, I have the product of two things equals 0. So at least one of those two things must be 0. I either have x plus 2 equals 0 or x minus 4 equals 0. And I address each of these individually. Solving x plus 2 equals 0, pretty simple, just subtract 2, x equals -2, or add 4. And so my solution is x equals -2 or x equals 4. As a little side note, depending on your instructor, some folks are fine with you just leaving this as the answer. Some folks want you to write something like the solution set is, and then these like curly braces, -2, comma, 4, something like that. So this is like an alternative way to represent this solution as a list of numbers that are all solutions. Okay, so let's take a look at these two exercises. And there's also kind of a follow-up question here. So do the two exercises, then look at the follow-up question and give it a few minutes thought. But we'll take about, I think about 5 minutes for these should be enough, including this extra question at the end here. Give a bit of thought to that one. All right, so I will be back in 5 minutes and we'll discuss the solutions. Okay, so taking a look at these two, we saw that for both of these, we end up with a left-hand side that cannot be factored over the integers. So I was focusing on exercise 1 here. Um, and the question is, okay, if we're not able to factor over the integers, does that mean that there are not any solutions? Can we make an argument that maybe there are solutions even though we can't find them with these methods? Can we argue that there actually are no solutions to exercise 1? How might we move forward with this? So let me switch my share here. And to kind of wrap up our discussion of quadratic equations, I want to take a look at the graphing calculator. So we have x squared plus x equals -5, or that's really x squared plus x plus 5 equals 0. Now I can choose to work off of this version of the equation. It's just a little easier uh, for me to deal with because kind of all of the complexity is on the left-hand side. But remember, what I'd be looking for here is a value of x, where when I plug that value of x on the left side, it ends up being the same as the right side, 0. So what I actually could do is jump over here in my calculator and make that a +5. I could type in x squared plus x plus 5. And what my calculator will effectively do when I ask it to graph this is it will plug in a whole bunch of x's, get a whole bunch of values for the left side, associate the x inputs with the y outputs. And then I can look at the graph and see if any of those, inputs seem to match y equals 0 for their output. I can jump over here to window, set everything to -10 to 10. That's usually a pretty good window to start with. And I can graph. And I actually see by graphing that it's pretty clear that there are no solutions here, right? Let me screen cap. Oh, I always forget to change my, to click on OneNote before I do my shortcut keys to screen grab, because otherwise it uh, makes the calculator leave that window before I can get the screen grab. There we go. Right, so these are the output values of the left-hand side for different input values x. And I'm looking for an input value that yields an output value of 0. Or in other words, I'm looking for an intersection of this curve with this line y equals 0 with the horizontal axis. And I see no intersection there. Remember, when we were graphing linear equations, we were looking for a point of intersection between those two lines. But these quadratic equations are actually, their graphs look like curves. So they look like this kind of maybe U shape or like an N shape, like an inverted U. Now, on the other hand, what if I had, instead of a +5 here, if I had a -5? I'm looking for two numbers that multiply to -5 that add to 1. Well, they have to be opposite signs, and the bigger one has to be positive. So I'd have to have +5, and -1 would be the only possibility. But that would add to 5 minus 1 is 4. So even for x squared plus x minus 5 equals 0, I'd be in the same situation. I can't factor this over the integers. If I come over to my graphing calculator though, and I change this to -5, here I actually do have solutions. I see that there are, let me do this the right way. There we go. Oh, I see that there are two inputs that yield an output of 0. Why didn't I find them with this method? Well, this method is only really able to find solutions, let's say roughly speaking, solutions that are like integer solutions. There are some more general methods for solving quadratic equations that can, in some sense, like solve all quadratic equations. Um, but those are a little more advanced. Those are not going to be covered in this course. So for instance, there's the quadratic formula, or there's completing the square. Those are more advanced methods that don't rely on our ability to factor a quadratic over the integers. So we kind of have a tool in our toolbox. It's a little bit like maybe a flathead screwdriver, right? It's like we can screw in some kind of screws, but not all screws, right? The screws that have the little like square drive, or that are like a Phillips head, that's a small Phillips head. We can't screw those in with our flathead screwdriver, but some, the flathead screws we can screw in, right? There are some quadratic equations we can solve now, but the inability of this method to solve a given quadratic equation, I think it's important to realize that uh, the inability of this method to solve a specific quadratic equation does not imply that that quadratic equation has no solutions. It just means those solutions don't um, uh, aren't able to be found with this method. So I think that's an important detail, an important nuance. And just also a reminder that we can look at the graph as well. We focus, quite a bit more on the algebraic side of things here, but the graphical side can be quite valuable as well. All right, let me switch my share back. Okay, so are there any questions on chapter 7 on quadratic equations? All right, so moving into chapter 8 now, rational expressions and equations. All right, let's start with the definition of a rational expression. Sorry, I'm moving my windows around here, getting things relined up. Okay, let's start with the definition of a rational expression. So we look at this and we see, well, rational, maybe that makes us think of like rational numbers, like that are fractions. Or maybe we even see as a component of this word ratio makes us think of division. So a rational expression is an expression that has something to do with division. And in fact, it's the quotient of two polynomials. So what is a rational expression? It is our quotient of two polynomials. This could be something as simple as like x over 3. X is a polynomial. It's a pretty simple polynomial, just a monomial. Even the number 3 is a polynomial, or more specifically, a monomial. Even a number like 1/2, that's actually a rational expression, believe it or not, like in some sense, right? But we can have, so this would be like um, a linear monomial, or a constant 1/2. We could have more interesting ones as well. Say 1 over x. This one is a little more interesting because we see that this isn't a maybe like more standard type of function. It's not just number times x, or it's not just a constant. 1 over x, we see that, well, the first thing we might see is that what numbers can I plug in? What numbers am I allowed to plug in to something like 1 over x? I could plug in like 7 and get 1/7, or -3 and get -1/3, but I can't plug in 0. That's the first thing that I realize, is that sometimes with these rational expressions, they come with a set of restricted values, a set of real numbers that I'm not allowed to plug in. Even when we were looking at things like quadratics, well, x squared plus 4x plus 18, I can plug any real number I want into, say, that quadratic expression, no problems. A linear expression, same thing. I can plug anything I want into it. But sometimes with these rational expressions, we end up dividing by 0 if we were to input certain values, so we can't input those values. I could have something like 3 over x minus 1 as another example. And I see here I have a restricted value of x equals 1. X cannot be 1, or else we'd be dividing by 0. Or I could have more complicated rational expressions. Something like x plus 1 over x squared minus 4. Something like a binomial over a binomial. Here I see that the denominator will be 0 if I were to plug in +2 or -2. So now I have a set of restricted values. I have more than one value, more than one real number that's not allowed to be plugged in to this rational expression. Otherwise, we'd be dividing by 0, and that is undefined. Or we could have something like, say, a cubic over x to the 5th power plus x cubed minus x squared, something like that. I do notice that in this denominator, I cannot plug in x equals 0. Everything in the denominator has an x in it, all of the terms. But this is actually a x to the 5th power. It's kind of hard to figure out what the other restricted values would be, if even there are any. There might not be any more. There might be more, and they might be hard to find. So we could have everything from kind of a very simple, almost trivial example up to a very complicated example. And as is typical, we're going to take a look at rational expressions, uh, looking at how to evaluate them, and looking at operations on them. And that's what's going to comprise most of the rest of our course material. So let's take a look at this example. Determine the values for which each rational expression is undefined, and we call these restricted values. So when we're searching for restricted values, we're looking for when is the denominator equal to 0. For what inputs would the denominator be 0? Those are restricted values. Those are values that were restricted from plugging into the expression. So here I would set 4x equals 0. This, of course, implies that x equals 0. This is our one and only restricted value for this rational expression. Something really important to notice is that when we're finding restricted values, we couldn't care less what's in the numerator. We had 7x squared minus 2x plus 1. If we had something else in the numerator, we'd have the same restricted value. We only really care about what's in the denominator. For my second example here, again, I pull off the denominator, x squared minus 1, and I ask, when is it 0? I noticed that this is a quadratic equation, right? So good thing that we did our kind of warm-ups here, reminding ourselves how to solve quadratic equations. I want to factor the left-hand side. I might recognize this as the difference of two squares, x squared minus 1 squared. So this factors as x minus 1 times x plus 1. And then equals 0 comes along. Well, this tells me either x minus 1 equals 0 or x plus 1 equals 0, either x equals 1 or x equals -1. So x equals plus or minus 1. These are my restricted values. Now, something that's maybe a notational oddity at first, it seems like, kind of over here in my scratch work, I found the solution, x equals plus or minus 1, to when the denominator is 0. But if I was going to append that to my rational expression, I would probably write something like comma x not equal to plus or minus 1, making the note that, what I found, the solutions that I found, are the numbers that I do not want to plug in to my rational expression. So, why did I write x equals plus or minus 1 in one case and x not equal to plus or minus 1 in another case? Well, because x equals plus or minus 1 is in the context of what numbers make the denominator 0, plus or minus 1. Those are the numbers I do not want to plug in to the rational expression. Right? So kind of depending on context, I might write it with an x equals. If you say, what are the restricted values? Plus or minus 1 are the restricted values. Or if you say, what real numbers do you not want to plug into the rational expression? Well, we would not want to plug in plus or minus 1, because that would give us a divided by 0. Okay, let's think about simplifying rational expressions. We know that a rational expression is, kind of roughly speaking, a fraction. And one of the things we're concerned with just fractions dealing with numbers is simplifying them, writing them in simplest form. So if I think of something like 6/8, this is a fraction. I suppose we could say that it's a rational expression. It's kind of a degenerate rational expression. But I look at 6/8 and I realize that I could really write 6 as 2 times 3 if I so chose. And I could write 8 as 2 times 4 if I so chose. I have a nice multiplication property for fractions that I can, in some sense, use in reverse. I can make 2 times 3 over 2 times 4. I could split off that 2 over 2 and make this 2 halves times 3/4. But 2 halves I recognize as just 1. This is 1 times 3/4. And 1 times something is just that thing. That's just 3/4. Right? Or the quick way of doing this is we break out a factor and we see we have a common factor. We just divide them out. That's kind of the shorthand method for doing all of this more detailed work. So I can write 6/8 as 3/4 because I have a common factor of 2 in the top and the bottom that I can divide out. Very importantly, maybe I'll write this in red because this is not a legal operation. Very importantly, if I was to do something like, oh, I don't know, like 3/4 and try to write this as like 3 over 1 plus 3 and like divide out the 3's, right? Can I do this? No, I can't. I can divide out common factors. If I have a thing that's multiplied by everything else in the numerator, and that same thing that's multiplied by everything else in the denominator, if the overall operation is multiplication, I can divide out. But if the overall operation is addition like this, I cannot divide out. And you might look at this and think, oh, that's silly. I would never make that mistake. That's so obvious. It might be kind of obvious when we're looking at numbers, but when we're looking at rational expressions and when things get more complicated, sometimes, right, when we're focusing more on the higher level complexity stuff, uh, some of the like lower level operations, we can tend to forget about them. So we want to make sure that if we're doing the kind of dividing out operation, that we have a thing on the numerator that's multiplied by everything else in the numerator, and a thing on the denominator that's multiplied by everything else in the denominator. The operation connecting them has to be multiplication, not addition or subtraction. So if I have numbers like this, like 6/8 can be split into 2 times 3 over 2 times 4 and then divided out. Could I have something like this? Say a factor of x plus 1 times 3 over a factor of x plus 1 times 4, and then divide these out and get 3/4. And the answer is essentially yes. There is a little caveat here that we'll discuss in more detail in a minute, but essentially yes. Yes-ish. With one little caveat dealing with those restricted values. But uh, for now, we want to just think that, okay, this kind of at a base level works similarly. We can divide out numbers in the numerator and denominator that are common factors. And we can divide out common factors that have variables in them. That's okay as well. In fact, we already kind of did this when we were discussing monomials, right? Simplifying monomials. Or even if I had, say, 3 times x plus 1 divided by x plus 1 times x plus 2, I see my common factor of x plus 1 in the numerator and denominator, and I can write this as 3 over x plus 2. And again, this is more or less correct. There's, again, a little detail with the restricted values we might have to clean up, but this is essentially correct. So when we're simplifying rational expressions, this is kind of what we're talking about. We're looking for common factors in the numerator and denominator that we can divide out and make the rational expression simpler. Okay, yeah, I think before I jump into any more, let's go through this exercise. So we have 3 problems here, and this one just determine the values for which each rational expression is undefined, find the restricted values for each of these 3. And then we'll continue on with our discussion of simplifying rational expressions. So since there are 2 quadratic equations to solve here, let's take about 4 minutes for this one. So take about 4 minutes, just find the restricted values, and then we'll discuss the answer. Okay, it's just about 4 minutes, so let's take a look at these three exercises. So for the first one, x squared minus 4 over 3x minus 1. Again, when we're looking for restricted values, we don't care about the numerator, we only care about the denominator. We want to restrict inputs that would make the denominator 0. There was a question in chat about what about the numerator? Well, if the numerator is 0, we might get something like, say, 0 over 4, but 0 over 4 is just 0. We can handle that perfectly fine if we get just a numerator of 0. The problem is if we got like 2 over 0, this doesn't make sense. This is undefined. So that's really what we're looking to avoid here. It's just when the denominator is 0. So for the first one, when is 3x minus 1 equals 0? That's just a basic linear equation. We add 1 to both sides, we divide by 3. We get a restricted value of 1/3. For the second one, we have a quadratic equation to solve. Oh, I forgot my equals 0 here. X squared plus 3x plus 2 equals 0. And that left-hand side factors into x plus 2 times x plus 1 equals 0. And we see that either x plus 2 equals 0 or x plus 1 equals 0. So either x equals -2 or -1. Those are our restricted values, -2 and -1. And then for the third one, another quadratic equation to solve, x squared minus 3x minus 28 equals 0. A little bit more complicated for this one, might have been a little harder to do, say, a guess and check method. We might have moved to the M and N method. We noticed that we want two numbers that multiply to -28, so they have opposite signs, and then add to -3, so the larger one has to be negative. And going down our list, we see that +4 and -7 fit the bill. So this factors into x plus 4 times x minus 7 equals 0. So then either x plus 4 equals 0, making x -4, or x plus 7 equals 0, making x +7. Be a little bit careful. I think I might have mentioned this in the quadratic equation section, but it can be a little tempting to just think that you can just grab m and n and have those as the solutions, like +4 and -7. But notice you'd have a sign error in both cases. So we do actually want to follow all of the steps and make sure that we do everything right and get all of the signs correct. But x equals -4 and +7 are the restricted values. Okay. Any other questions on these? Okay, now let's look at simplifying rational expressions. So we'll take a look at this first example, 5x plus 5, all divided by 6x plus 6. Now my goal is to see if I can find common factors like this. And you might have guessed one of the key principles in finding common factors is factoring, right? Is actually taking whatever expression we have and factoring it. In fact, that's kind of what we did here, right? If we wanted to go to the most extreme conclusion, we could actually write out a full prime factorization for our numerator and denominator, and then divide out all common factors, and then kind of maybe put everything back together at the end. Now, we didn't have to do that because we kind of intuitively get that 4 is 2 times 2, and that shares no common factors with 3, but we could have broken 8 out as 2 times 2 times 2, 6 is 2 times 3, gotten a full prime factorization for both, divided out any common factors, and then if needed, multiply them back together, whatever is left. If we do a similar thing here, if we factor everything out, I look at my numerator, 5x plus 5. Well, that has a greatest common factor of 5. That can factor out. And 6x plus 6 has a greatest common factor of 6. When that factors out, that leaves me with x plus 1 as well. And I see I have a common factor of x plus 1 in the numerator and denominator. I have x plus 1 times something in the numerator, x plus 1 times something in the denominator. These can divide out to give me 5/6. Now, I said earlier that this is almost correct. It's kind of like morally correct, right? But there's a technicality here that we need to deal with. So if I plug, let's say, x equals 1 in the left-hand side, what do I get? 5 plus 5 is 10 over 12. And we see that is equal to 5/6. Right? 10/12 simplifies down to 5/6, and that's exactly what we said it was equal to. All kind of seems right with the world if I pick x equals 1 to plug in, or if I pick x equals 7 or -12 or something like that. But what if I try to plug in x equals -1? Well, then my numerator would be -5 plus 5 is 0, and my denominator would be -6 plus 6 is 0. Is this equal to 5/6? Well, no, 0 over 0, I really don't know what to do with. I certainly don't want to say it's equal to 5/6. I have a restricted value here that x cannot be -1. In other words, this expression is equal to this expression. They are the same value only when x is not -1. Right. I always want to be careful to explicitly state any domain restriction when I'm doing the simplification. Why is that? Why didn't I have to state the domain restriction over here? Well, when I have 5x plus 5 over 6x plus 6, it's implied. We can see by looking at the algebraic expression, or maybe not instantaneously looking at it, but we can see by working with that expression that x equals -1, or that we can see that -1 cannot be substituted in for x legitimately. It's an implied domain restriction. But over here, if I think of 5/6 really as an expression in x that just doesn't happen to have any x's explicitly showing up, I don't see any domain restriction on x. There's nothing suggesting to me that I shouldn't be allowed to plug in or to consider what happens when x is -1. So if I just wrote 5x plus 5 over 6x plus 6 equals 5/6, that wouldn't be correct, because when I plug in x equals -1, those two things are not equal. So these are equal if and only if x is not equal to -1. So let me write this a little more cleanly, just so that I can, because I scribbled on this like John Madden or something. Um, Let me write kind of closer to exactly what I would write if I was being careful here. This would be 5 times x plus 1 over 6 times x plus 1 equals 5/6. But under the caveat that x cannot be -1. Right? I have a similar problem here. X squared minus x minus 12 over x squared minus 8x plus 16. I have a ratio of two quadratic expressions. So the first thing I want to do is factor these. I want to factor the numerator, factor the denominator. Let's come over here in scratch work and do each of these. X squared minus x minus 12, looking for two numbers that multiply to -12 and that add to -1. I think kind of 4 and 3 might fit the bill, like say -4 and +3. If I multiply those out, does that work? I get x squared from the firsts. From the outsides, I get plus 3x, and the insides minus 4x. That's out to a -1x. That's looking good. And then my last multiplied at -4 times +3 is -12. So yeah, I think that is good for the numerator. And then what about the denominator? I need two numbers that multiply to positive 16 and then add to negative 8. I think that is negative 4 twice. I could write it as x minus 4 squared, or I could write it as x minus 4 times x minus 4. Right, my first give me x squared minus 4x is minus 8x from the outsides and insides. And then the last gives me minus 4 times minus 4 is plus 16, exactly what I wanted. I see I do have a common factor of x minus 4 on the top and bottom. X minus 4 times x plus 3 on the top, x minus 4 times x minus 4 on the bottom. So I can divide out those x minus 4s, leaving me with x plus 3 over x minus 4. In this case, I can probably get away with not writing the domain restriction because what's my restricted value here? X cannot be positive 4. But I actually still have an x minus 4 showing up in my simplified form. Could I get away here with not writing x not equal to 4? Yeah, probably, because it's still implied in the end result. But just, as a matter of form, it's just always better to write your domain restriction explicitly, just to be clear about what is not allowed to be plugged in. So I probably still would write it here, even though maybe I could technically get away with not writing it. But I find that, the mistake that people make most often with these, even at the calculus level, is they forget about the restriction here when it is important in, say, a situation like that. And, it might seem like a minor technicality, but, you can ask students who have gone through Calc 1. This is actually uh, a really important idea in calculus even. And students often forget about this technicality, but it becomes much more important later on. Okay, so let's look at these three exercises. So in each of these, we're going to work through simplifying. So first, factoring the numerator, factoring the denominator, looking for any common factors, dividing out common factors, and noting our restricted values along with that simplified form. So let's take about 8 minutes for this. These rational expression problems are a bit lengthy, but if you break them down into simple components, look at the numerator, factor it, look at the denominator, factor it, look for restricted values, look for anything that can divide out, write your answer. It's not too bad if you take it step by step. So let's take about, what did I say, like 8 minutes for these three. I think that should be enough time to work through all of these. Okay, it's just about 7 minutes. Let's take a look at these three. So the first one, we have the ratio of two linears. So really the only interesting thing we could do is maybe factor out a greatest common factor. And indeed that works here. We can factor an 8 out of the top to make 8 times x minus 12, and a 3 out of the bottom to make 3 times x minus 12. And we see from this factored form, the denominator will be 0 when and only when x equals 12. So we'll note our restricted value that x cannot be 12. And then we'll proceed with dividing out common factors. The x minus 12 in the numerator and denominator can divide out, giving us a simplified form of 8/3 with the caveat that x cannot be 12. For the second one, we factor a numerator and denominator. I think this is easy enough to do by guess and check. We see that the numerator factors into x plus 5 times x minus 1, and the denominator into x minus 1 times x minus 1. And again, we note our restricted value. Looking at the denominator, we just have 2 copies of x minus 1, so that's only going to be 0 if x equals 1. So we have a restricted value, x equals 1. And then we divide out common factors. We get rid of the x minus 1 in the numerator and denominator. We're still left with one of the x minus 1's in the denominator, though. We only divided out one of them. So we end up with x plus 5 over x minus 1, again with the restricted value, x not equal to 1. And then for our third example, we see a numerator and denominator again that are quadratics. So we're going to look to factor them. We notice that the numerator is a difference of two squares, x squared minus 2 squared. We factor it into x plus 2 times x minus 2. And the denominator, we might have been able to do guess and check, or we might have had to go through the factoring process. But either way, we end up with x plus 8 times x minus 2. Again, I look at my denominator here to find my restricted values. X cannot be 2 or negative 8. And then I go ahead and divide out any common factors. The x minus 2's divide out here from the numerator and denominator, leaving me with x plus 2 over x plus 8, with the restriction that x cannot be 2 or negative 8. Any questions on these? So there's certainly a lot going on here, but again, I think each step is pretty manageable. It's just a case of not getting overwhelmed, not looking at, don't look at the whole problem and think, oh, wow, this is such a big problem to do. Take it one step at a time. Can you factor the numerator? Check that off. Can you factor the denominator? Check that off. Now that you've got the denominator factored, can you find the restricted values? When is the denominator 0? Check that off. And then can you divide out common factors and then put it all together at the end? Okay. And let's look at another example here. So here we actually have a ratio of cubes. X cubed plus x squared plus x plus 1 over x cubed plus 1. We've talked a good bit about factoring quadratics, but not too much about factoring cubics. So unless something pretty nice works out here, we're not going to be able to do much with this. However, this does look like it might work out pretty nicely. If I look at my numerator, one kind of clue that I have here is there are 4 terms in my numerator, and none of them are like terms. It's not like I can combine any of these together to make things simpler. This is as simple as it gets. But I know that with 4 terms, that maybe is an indication that factoring by grouping might work. Let me split off these first 2 and the last 2 and consider them separately. From the first 2, x cubed plus x squared, I can factor out an x squared times x plus 1. And from the last 2, plus x plus 1 is just, well, really plus 1 times x plus 1. And hey, that worked out nicely because now I have a common factor of x plus 1 that can further factor out. And now I want to ask myself, so I've got a factored form. I want to ask myself, can I go any further? Right? If I have 8 and I split it into 4 times 2, I could split the 4 into primes as 2 times 2. So, right, can I continue going here? X plus 1, that can't be factored any further. X squared plus 1, it almost looks like a difference of 2 squares, which I could factor, except that it's the sum of 2 squares. X squared plus 1, that doesn't factor. So my numerator factors in x plus 1 times x squared plus 1. Okay. So that's one piece, right? I factor the numerator. Let me look at the denominator, x cubed plus 1. Now, again, this is a cubic. There are pretty limited situations where I know how to factor a cubic. But one of them was the sum of 2 cubes, and I do recognize this as x cubed plus 1 cubed. I know this factors into x plus 1 times something. What does the x have to hit to make an x cubed? That's got to be an x squared. What does the 1 have to hit to make a plus 1? That has to be a plus 1. And let me look at what I would have here. I'd have x times x squared gives me x cubed. X times 1 gives me plus x. 1 times x squared gives me plus x. I'll write it in a different column here. Plus x squared. And 1 times 1 gives me plus 1. This and this are what I want to keep, but I got to get rid of that plus x and that plus x squared. I do that with a minus. And well, I think a 1 times x or just an x will work here, right? This x times negative x gives me a negative x squared. And this negative x times 1 gives me a minus x. Canceling this, canceling that. I've gotten rid of exactly what I want to get rid of, kept exactly what I want to keep, and this is my factored form. I kind of know that when I factor a sum or difference of cubes, once I get this form, it doesn't factor any further. So this one is prime, this quadratic, just based off of basically previous knowledge. But you know, you could check it if you wanted to. It's not going to factor. X plus 1 times x squared minus x plus 1. We see we have a restricted value. X cannot be 1. And then we can divide out the x plus 1s. And that is our answer. Along with that domain restriction, x cannot be 1. Right, so in a problem like this, each of the individual steps was a little more complex, was a little more challenging. But I think the overall strategy wasn't too bad, right? If we just chip away at it one piece at a time, maybe this factorization was a little harder than, say, you know, just factoring this difference of 2 squares or something. But that was just that one component, right? That one little piece of the puzzle took a little bit longer, but it was manageable, and we could plug that piece back in. So I think with rational expressions, there's a lot going on, and it's easy to get maybe overwhelmed if you kind of look at the whole problem globally. But if you focus on, okay, you know, if you start to go that route and you start to get overwhelmed, ask yourself, okay, what is one thing I could do? You know, I could factor the numerator. Like that's a manageable, you know, bite-sized chunk of a problem. What's another thing I could do? I could factor the denominator. I do that, plug it in. What's another thing I could do? I could determine what the restricted value is. What's another thing I could do? I could look for common factors and divide them out, right? So if you take it one step at a time like that, I think it's a little more manageable. Okay, so 2 last exercises. Simplify both of these. So we'll take maybe about 7 or 8 minutes here. let's actually make it about 8 minutes because these are not the easiest to factor. Um, make sure that you factor everything completely, and then we'll come back and discuss the answers in about 8 minutes. Okay, it's just about 8 minutes, so let's take a look at these ones. So for the first one here, we will start with just factoring the numerator. We see that we can factor it by grouping, and it factors into x plus 3 times x squared plus 4. Note that obviously x plus 3 doesn't factor any further, and x squared plus 4 is a quadratic, but it's the sum of two squares, not the difference of two squares. It doesn't factor any further either. Our denominator x squared plus x minus 6, we could either use guess and check here or go through the m and n method, but we get x plus 3 times x minus 2. That's what our denominator factors into. We can identify pretty quickly that the restricted values for the zeros of the denominator are that x cannot be -3 or +2. Either one of those input would make the denominator 0. Once we've identified our restricted values, we divide out that common factor of x plus 3 in the numerator and denominator. No other common factors to divide out. That leaves us with x squared plus 4 divided by x minus 2 with the restriction x cannot be -3 or +2. As a side note, I don't remember if I explicitly said this or not, but we always want to find our restricted values before dividing out. I think I might have implicitly kind of done that all along. I don't remember if I explicitly mentioned it, but of course, if we divide out a bunch of stuff and then look for restricted values, we're likely to be led astray because we might have gotten rid of some of the important factors in the denominator. So we find the restricted values before dividing out, so that we make sure to get all the restricted values and we don't miss any. And then our last one here, x to the fourth minus 1 over x squared minus 1. We might have done x to the fourth minus 1 equals x squared minus 1 times x squared plus 1, and then look to divide out the x squared minus 1 on top with the x squared plus 1 on the bottom. And that would be valid, except it's a little bit hard at this point, before we fully factored everything, to tell what the restricted values are. So if you notice something like that, you can use that point that, if we had wanted to, we could have written this as what, x squared minus 1 times x squared plus 1 over x squared minus 1 and divided these out, provided that we are confident that we could evaluate x squared minus 1, the denominator, and figure out what the restricted values are. But the kind of standard way to do it would be to note that x squared minus 1 factors further. X squared plus 1 does not factor any further, but x squared minus 1 factors into x minus 1 times x plus 1. We could just fully factor the numerator that way, fully factor the denominator as well. We see we still get everything canceling out as it should, but it made it easier for us to identify the restricted values of 1 and -1. In this case, actually, our denominator completely divides out with the numerator. X minus 1 and x plus 1, both of those factors can divide out, leaving me with only the x squared plus 1 left in the numerator. Effectively, what I have is x squared plus 1 over 1, but anything over 1, we can just get rid of that over 1. So I just have x squared plus 1. But again, with the domain restriction, x cannot be plus or minus 1. If I only wrote x squared plus 1, implicitly, that would suggest that I can plug any real number into there. I just take that number squared, add 1. There are no problems. But of course, these can't be equal. Say 1x equals +1, because on one hand, I get 0 over 0, and on the other hand, I would get, well, 1 squared plus 1 would be 2. And 0 over 0, something that's indeterminate, can't be just equal to 2. That doesn't make sense. So we need to be sure to put our domain restriction in there. All right, any questions on the material from today? So that was our first foray into chapter 8. You can see that the material is getting a little more complex. So, reading ahead a little bit is probably a good idea. Also, if you were a little bit lost in chapter 8 today, I would say maybe one thing to do is take a look back at chapter 7. I mean, obviously that's good for review for the exam this week, but also because you see that chapter 8 relies so much on chapter 7 with factoring, with solving quadratic equations, figuring out when the denominator is 0 and so on. If you're not really solid on the chapter 7 material, then chapter 8 is going to be even more confusing. So if you're struggling with chapter 8, do a good review of chapter 7, both for the exam and for preparation for Thursday's class. Okay, so with that being said, I will stop the recording.